6.207 volts, 700.49 milliwatts, from 900 square centimeters of plain asphalt, a patch smaller than a kitchen table. Something under that patch treats summer heat as fuel, not damage, turning a road's temperature gap into current in a wire. Engineers call it a road thermoelectric generator, the densest version ever published, 70% denser than anything before it. You heard that right. That is not a lab concept behind glass. It is a certified result from Chang'an University, published in Renewable Energy 2022. Here's what that means in plain English. Your city's roads bake hot enough to soften every summer, and until now, that heat only cost money. And that is just the beginning. Self-powering roads. Hit a quick like and subscribe so you do not miss what's next. By video's end, you will understand how a road becomes a power source. For decades, heat and pavement had exactly one relationship worth studying: how much damage the heat was doing. Civil engineers measured asphalt the way a doctor measures a fever, as a problem to manage, never as an asset to use. Summer sun can push a road surface to 60 or 70 degrees Celsius, roughly 20 degrees hotter than the air around it. That heat softens the binder holding the asphalt together, and softened asphalt deforms under truck tires until it ruts, cracks, and needs repaving years ahead of schedule. Every one of those repaving cycles costs a transportation department real money, funded by taxpayers who never see the heat itself as the culprit. Multiply that cycle across a single city's entire road network, year after year, and the recurring repair bill starts looking less like routine maintenance and more like a cost nobody ever thought to question. Cities treated this as the cost of doing business. Nobody budgeted for that heat to pay them back. You have felt the version of this that actually touches your life. The summer afternoon when your city asks everyone to conserve power because the grid is straining, on exactly the kind of day when every road for miles is radiating heat into the sky and doing nothing else with it. Here's what most people get wrong about wasted heat. It is not that nobody noticed it. It is that nobody thought the gradient was big enough to bother with. That changed with an engineer named Jang at Chang'an University's School of Highway Engineering in Xi'an. In 2017, Jang's team built something almost embarrassingly modest by comparison to what was coming: a slab of asphalt no bigger than a card table, fitted with a thermoelectric generator, and tested through a full winter and summer cycle. In winter, it produced about 0.4 volts. In summer, with a bigger heat gap to work with, it inched up to 6 or 0.7 volts. That is barely enough to register on a household multimeter, the kind of reading an engineer might dismiss without a second look. Most engineers looking at those numbers would have filed the idea under interesting, not useful, and moved on. Jang did not. His stated bet, laid out plainly in that first published paper, was that the temperature difference baked into ordinary pavement was a legitimate, untapped energy source. Not a curiosity, not a stunt, but infrastructure nobody had bothered to switch on. That distinction between a curiosity and infrastructure is what separated Jang's project from every prior attempt that quietly ended after one promising measurement. Picture a furnace running all day with the flue wide open, heat pouring out into the sky, completely unharvested, doing nothing but warming the neighborhood. That is every paved road on the planet, every single summer. Jang's team calculated something else in that first paper that made the idea worth chasing seriously. Scaled up, a single kilometer of road, 10 meters wide, could theoretically produce around 160 kilowatt hours of electricity in 8 hours of sunlight. That number is the whisper that started this story. But a whisper is not a proof, and the wider engineering world was not going to take a fraction of a volt prototype seriously without a fight. This idea is older than Jang's lab, and that matters. A Japanese researcher named Meishirashi first proposed pulling electricity out of pavement heat back in 1997. A colleague named Seebeck actually built and tested a version of it in 2006. For a full decade after that, the concept sat almost untouched, filed by most of the engineering world next to other interesting but marginal renewable ideas, dismissed as too inefficient to matter next to solar panels or wind turbines, which were already producing real bankable power. A decade is a long time for a working idea to sit on a shelf, and it tells you exactly how steep the skepticism was. Long enough for an entire generation of civil engineers to graduate having never seriously considered pavement as anything other than a structural surface. They said the same thing about early solar cells. We all know how that ended. Here is where the consensus broke. Rather than treating the small thermal gradient as a dead end, Jang's group at Chang'an ran the problem through finite element simulation first, modeling exactly how heat actually moves through an asphalt slab, layer by layer, before building anything physical. Only after the simulations pointed to a workable structure did they fabricate real prototypes and run them outdoors through actual Xi'an seasons, not a climate chamber. That distinction matters. A climate chamber can be tuned to flatter a prototype, while an actual Xi'an winter and summer cannot. The engineers knew the gradient was small. The question was whether anyone would listen to what they thought they could do with it anyway. But here is the thing. As modest as that first prototype was, it was never meant to be the finished idea. It was the proof that the gradient could be engineered around at all, and what came next was built specifically to make the skeptics look premature. Here's the part that changes everything. The actual physics is almost insultingly simple. Take 2 points at different temperatures, connect them through the right material, and electrons start moving from the hot side to the cold side on their own. No moving parts, no combustion, nothing to wear out. That is the Seebeck effect, the same principle that has quietly powered NASA's deep space probes for decades, running off nothing but the heat of a decaying isotope, keeping instruments alive in places sunlight can never reach. Jang's team was applying the exact same physics to something far less exotic, a stretch of highway. The catch is scale. A spacecraft's heat source can be engineered to stay hot indefinitely. A road cannot. Its usable temperature gap runs about 15 degrees Celsius in winter and 25 to 30 in summer. The difference between the baking surface and the ambient air above it, and that gap is what the whole system has to work with, nothing more. Every watt the system ever produces has to come from that narrow window, which is exactly why the engineering around it matters so much more than the physics itself. A wider gradient, harvested cleanly, is worth more than a clever material. And Jang's team understood that distinction before anyone had a working system to prove it with. To capture it, Jang's design uses 3 layers stacked with intention, a hot side plate near the road surface that pulls in heat. The asphalt was already absorbing for free, a thermoelectric generator module sandwiched underneath that converts the temperature difference directly into current, and a cold side module reaching down into the cooler subgrade soil or out to open air, so the gradient has somewhere to discharge into. This was the exact problem Jang had been circling since that first slab test. Not whether a road could generate any electricity at all, but whether a hot side and cold side pairing could be engineered efficiently enough, cheaply enough, and durably enough to be worth anyone's time. The modest readings from that first winter and summer were not a disappointment. They were proof the gradient was real and usable. The verdict was simple. If the physics worked on a card table, it could be scaled. But a working principle on a lab bench is not a working system. And the number that actually got this idea funded seriously was not the voltage. It was what happened when Jang's team stopped treating the cold side as an afterthought. Here is the brutal catch nobody accounts for. The hot side of this system is free. The sun does that work every single day with no engineering required. The cold side is not free. It is the actual bottleneck, and for years, the instinct across the whole field was to keep it as small and simple as possible, because smaller means cheaper and easier to bury under a road. Jang's team did the opposite. Instead of shrinking the cold side module, they multiplied its surface area, stacking multiple layers and adding fin-like structures to shed heat faster. The same logic used on a motorcycle engine, where fins are cut into the metal, specifically to grab more air and dump heat quicker. Fewer surfaces would have been simpler, cheaper, and easier to explain to a funding committee. It sounds like it should trap more heat instead of shedding it. That is exactly why it works. More surface area touching the cooler layer below means a wider, more stable gradient for the generator to draw from, and a wider gradient is the only thing that turns a whisper of voltage into a usable signal. That decision is what their team's own earlier results had already seemed to validate as unnecessary. A simpler cold side had worked fine in 2017. Reworking it anyway, on a design that already had a published track record, is the kind of choice that risks looking like fixing something that was not broken, and risks the credibility Jang's team had already built with the simpler version. It was not broken. It was just leaving power on the table. The result: 6.207 volts and 700.49 milliwatts from that 900 square centimeter test section, a power density 70% higher than the next best published design. And the road underneath survived the process. Chang'an's team ran it through 10,000 cycles per millimeter of dynamic load testing and measured a fatigue life of 246,000 cycles before failure. Durability numbers that put it in the range of ordinary pavement. Not a fragile lab experiment bolted to a highway. A road engineer reading those two durability figures alongside the power numbers is reading proof that this is not a trade-off between generating electricity and keeping the road intact. That is not a marginal improvement. That is the difference between a science fair demonstration and something a transportation department could actually specify in a contract. But a record-setting result is only half of the equation. A 900 square centimeter slab in a controlled test is not a highway. And turning one good patch into a working road system is an entirely different kind of problem. A single test slab is easy to get right. A real road is not one slab. It is thousands of them, strung together across kilometers, each one facing a slightly different angle to the sun, a different traffic load, a different drainage condition underneath. Coordinating all of that consistently is where a lot of promising lab technology quietly dies. Here is what most people get wrong about scaling an idea like this. The obvious move. Embedding the generator modules directly into the driving surface is actually the wrong one. Direct embedding exposes the thermoelectric material to the constant mechanical pounding of traffic, the exact kind of stress that shortens the lifespan of anything not designed for it. Jang's architecture instead places the working modules to the side in the subgrade layer beneath the load-bearing surface, where they collect the same heat without absorbing the same punishment. It is a small positional choice with a large consequence. The system stops competing with the road for survival and starts working alongside it, which is also what makes it possible to service or replace a module without tearing up a driving lane. A separate team at Chang'an University of Architecture and Technology arrived at a related answer independently, stacking their own generator modules into a multi-layer board rather than a single flat plane, squeezing more collection area into the same footprint of road without widening it by a single centimeter. Two separate university labs converging on layered, roadside architecture rather than flat embedded modules is not a coincidence. It is confirmation that the field had found the actual shape of the solution, arrived at from two different starting points and two different sets of assumptions. Think of it like a network of gutters draining into one collection pipe, rather than one oversized funnel trying to catch everything at once. Distribute the collection points, and the whole system becomes both easier to build and easier to repair one section at a time, without shutting down an entire stretch of road to fix a single failed module. A gutter that clogs does not take down the whole drainage system with it, and neither does a single failed collection point in this kind of distributed design. Scaled across a full kilometer of road, the numbers land in the same neighborhood as that very first back-of-the-envelope estimate from years earlier, enough to make engineers start asking a harder question. Before anyone treated a number like that as real for planning purposes, it needed independent verification, not just one lab's word for it. Here is the honest picture. This is not a technology that is about to power a city block, and no serious engineer working on it claims otherwise. What it is proven to do, certified and published, is generate meaningful, durable, low-grade power exactly where road infrastructure already needs it. Embedded traffic sensors, black ice early warning systems, and localized de-icing circuits that currently require their own separate power lines or battery replacement schedules. The trade-off is real, and stating it plainly is what keeps this credible. Per square meter, thermoelectric pavement is nowhere near as efficient as solar panels or wind turbines at converting available energy into usable electricity. Nobody is proposing to replace a solar farm with a parking lot, and no honest engineer working on this technology has ever framed it that way. The advantage here is not raw output, it is location. Power generated at the exact spot where the sensor or the safety system already sits, with no cabling run required back to a substation, and no battery that needs replacing on a maintenance schedule. For Jang, that is the actual vindication. His original bet, back in 2017, was never that a road slab could outproduce a power plant. It was that heat the entire industry had been writing off as pure liability was in fact an asset nobody had bothered to switch on. The certified result does not just validate a voltage reading, it validates the premise his whole career had been built around, that waste is often just a resource someone has not engineered for yet. That is not an incremental improvement to road maintenance. That is a redefinition of what a road is allowed to do. If a published result like this changes how you look at the pavement under your own car, the next material breakthrough in this series is going to be even harder to believe. Hit subscribe so you are there when we cover it. Here is a number that puts this in perspective. There are more than 60 million kilometers of paved road on this planet, nearly all of it absorbing solar heat every day and returning none of it as electricity. Even a small fraction of that surface fitted with this kind of system represents a genuinely enormous, currently untapped resource, not for replacing power plants, but for making roads self-sufficient at the exact jobs they already need power for. The sectors where this actually matters first are not glamorous, and that is precisely the point. Smart highway sensor networks that monitor traffic flow and structural health in real time, remote road segments, far from any power grid that currently rely on solar panels or battery swaps, and winter road safety systems that need to detect ice and trigger de-icing without waiting for a technician to change a battery in a snowstorm. None of these applications need a power plant's worth of electricity. They need a small, dependable trickle delivered exactly where it is needed, without a wire running back to the grid, which is precisely the kind of demand this technology is already proven to meet, rather than the demand it was never designed for. Real adoption requires more than a good lab result. It requires a cost per kilometer that a transportation department can defend in a budget meeting. Integration with existing repaving schedules. So installation does not mean tearing up perfectly good roads and years of real-world durability data beyond a controlled fatigue cycling test in a university lab. That is a slower, less cinematic process than a single published paper, and it is the actual bottleneck standing between this technology and your street. The gap between a certified result in a journal and a line item in next year's infrastructure budget. The response from the broader engineering world has been exactly what you would want to see. Not one lab chasing a headline, but multiple independent programs. Chang'an University, Xi'an University of Architecture and Technology, and research groups well beyond China, converging on similar layered roadside architectures from different starting points. That kind of independent convergence is worth more than any single record-setting paper on its own. There's a historical parallel here worth sitting with. In the 1950s, early photovoltaic solar cells converted only around 6% of sunlight into usable electricity and were dismissed by most of the energy industry as a novelty fit only for satellites, far too inefficient and expensive for anything on the ground. Today, solar accounts for a meaningful and growing share of new electricity generation worldwide. The efficiency argument against thermoelectric pavement today is the same argument once made against solar. It was wrong about the ceiling then. It has been wrong about ceilings like this before, in field after field, whenever the argument against a new energy source was efficiency rather than physics. The limit here was never political, and it was never about which country gets credit for the idea. It was thermodynamic and economic, a small temperature gradient and a cost curve that needed years of engineering to bring down. That is the whole story, and it is the only story that matters. Here is the largest implication of everything you just heard. Infrastructure is starting to stop being purely passive. A road, a wall, a bridge deck, these have always been treated as inert surfaces that simply exist and slowly decay. This result is part of a broader shift where the materials underneath our daily lives are being re-engineered to do work they were never designed to do, using energy that was always there and always being thrown away. The road you drove on this morning was never designed to do anything but hold weight. That assumption is exactly what is now being rewritten, one published paper at a time by researchers who looked at something everyone else had already stopped questioning. If you made it this far, you now understand more about how pavement actually works than most people who write about infrastructure for a living. What was actually proven here is specific and bounded, and that is exactly why it is credible. A small thermal gradient, smaller than the one used in almost any other application of this physics, can be engineered into a durable, certified source of usable power at road scale. Not grid scale, but real, published, and road tested. That is the entire claim. No more and no less. And it is exactly the kind of bounded, modest claim that holds up under serious scrutiny. If this changed how you think about the road under your own car, a surface you cross every single day without a second thought, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Should cities require every new road project to include energy harvesting layers like this, even at extra upfront cost, or is this better left as a niche solution for sensors and de-icing until the efficiency improves further? I read every single one. See you in the next one.